Is it Friday? Okay, let's get started here. Chemistry 3111. This is chapter 24, where we're going to talk about carbohydrates. You could say it's the sweetest chapter of all. We're talking about sugar. So a couple things you need to recall before we get into the chemistry of carbohydrates is that you want to remember how to draw a chair conformation. You remember we spent a lot of time talking about, cyclohexane chairs like this. Well, now we're going to talk about chairs. Well, that's not a very good chair. We're going to talk about chairs with an oxygen in the ring because we have a six-membered ring with an oxygen in it when we draw the closed form of a molecule like glucose. We'll talk more about that later on. Haworth projections, of course. We're going to also look at sugars being represented as Haworth projections, and then you can shade in these bonds here to represent the ring and like it's kind of laying flat. Fisher projections, we're going to talk a lot about Fisher projections. So here's a Fisher projection of a carbohydrate. So if you put a hydroxyl at here, here, and here, then you fill everything out here. So you have a hydrogen here, a hydroxyl here, hydrogen, hydrogen. This is called D-glucose. It's the most common monosaccharide on Earth. Hemiacetals and acetals. So you should know that a hemiacetal is basically a carbon that has like an alcohol attached to it and an ether. Whereas an acetal is when you have a carbon that has basically like two ethers attached to it. So that's an acetal. And then, of course, the reduction of aldehydes and ketones with reagents like sodium borohydride. And I'm pretty sure that stuff is fresh in your memory. So, I mean, really, what are some of the things that you're going to want to think about? Of course, you might have to practice drawing your chairs again and incorporating an oxygen into the ring. And then, something else that we're going to look at is all these chiral centers in a molecule like D-glucose, what are their stereochemical configurations? Are they R or are they S, right? So those are things that you're going to want to know. Lots of stereocenters in carbohydrate chemistry. Well, carbohydrates, the word carbohydrate is actually kind of a historical term because if you think about the formula of glucose, and I'm sure that a lot of you have seen this in biology class, that it's C6H12O6. Well, it's like you have 6 carbons, and then it's like you have one water molecule for every one of the 6 carbons, right? You can kind of break it up into every every carbon rather has a water molecule associated with it. And that's where it comes up, or that's where we get the name carbohydrate. It's like each carbon has a molecule of water for every one of the carbons. But that again is historical because not all carbohydrates have this kind of formula where there's exactly one water molecule for every carbon. And so a more accurate description of what a carbohydrate is, and again, we call carbohydrates sugars for short, is that they're polyhydroxyaldehydes or ketones. Okay, so we're basically going to be looking at a whole bunch of different aldehydes and ketones, and they have lots of hydroxyls on them. What's a hydroxy, right? It's a hydroxyl group. Now, where do we get carbohydrates from? Well, most are going to be synthesized in nature, especially the ones that are naturally occurring. They come from carbon dioxide and water in the process called photosynthesis. I remember learning this in grade school, that you take, carbon dioxide, plants take it in, and then they take water and sunlight, and then they make sugar. And of course, not only do the plants form sugars in photosynthesis, but they also release oxygen in the process. And then, of course, we take the sugars and we break them down and we release carbon dioxide and water. Anyhow, how would we classify a carbohydrate? Well, the simplest types of carbohydrates are monosaccharides. And if you've heard of disaccharides and polysaccharides, those are going to come up later on in the class. But right now, for the first little while, we're just concerned with the simplest sugars, which we call monosaccharides. Now, a monosaccharide can contain multiple chiral centers. And because of that, we find that Fisher projections are often used to represent their structure. If you go back, just go back at this slide here, and you see this molecule that I have down here. This is glucose. Now we have, how many chiral centers here? We have 1, 2, 3, 4. But it is actually difficult to keep track of all those dashes and wedges on this, this straight chain form of glucose. So it's actually simpler to keep track of those chiral centers in a Fisher projection. And that's why Emil Fischer developed the Fisher projection. And I mentioned that back in chapter 5 of Organic Chemistry 1. So here we have the structure of glucose and fructose, and glucose, again, is what we saw on the previous slide. Here are the 4 stereocenters here, and this way we don't have to deliberately draw any dashes or wedges, and we don't have any of that stuff to sort of get organized. And what you're going to see is that later on we're going to look at all the different types of carbohydrates. They have an aldehyde at the top. We call these aldoses, and then these kind here, which we call a ketose. But anyhow, we're going to look at the families of sugars, and you're going to see how Fisher projections are just so powerful at representing different sugars. And so that's why, again, Emil Fischer developed the Fisher projection, was to actually make things a little bit simpler. So as you heard me say on the last slide, I said these 2 words, aldose and ketose. So you can probably guess where they come from. The aldose is a carbohydrate that contains an aldehyde group. And so we use the prefix aldo. So here we have an aldehyde, and so we use the prefix aldo. And then you see it says aldopentose because we use the terms di, tri, tetra, penta, hexa, hepta, so on and so forth to indicate the number of carbons. You can clearly see that there is a total of 5 carbons in this molecule. And so we would describe this as an aldopentose. If you look at the next compound, you see that it has a ketone functional group towards the top. And so it is some kind of ketose, and it has a total of 6 carbons. So we call it a ketohexose, again, because it has 6 carbons. And so you can classify monosaccharides as either being an aldose or a ketose. And then we use the terms di, tri, tetra, penta, so on to indicate the total number of carbons in the carbohydrate. All right, there we go. So let's move on from there, and let's talk about the simplest possible aldose that we could have, which is called Dglyceraldehyde. And I don't think it's a bad idea to actually memorize the structure of Dglyceraldehyde. And trust me, if you do all the practice problems that I recommend that are posted to Canvas, you'll get a feeling for what the structure of Dglyceraldehyde is here. So you see that it's got 2 ways of describing the molecule. It says positive glyceraldehyde here, and then it says Dglyceraldehyde on the left, and I'll talk about that more later on. But anyhow, glyceraldehyde, again, is the simplest possible aldose that we could have, and it has 1 chiral center. So there's only 1 chiral center in the molecule right here. Something that I want you to remember is that the bonds that are horizontal, remember that those are the bonds coming out towards you. Okay, those bonds are coming towards you. And the bonds that are vertical, those are the ones that are going back into the page or into the screen like this. So if we assign a stereochemical configuration, or if we try, right, the oxygen has the highest priority, the hydrogen has the lowest, this carbon has second, and this carbon has third. So we're going like this, which is counterclockwise. You might think, well, this is S. But remember, since the hydrogen is coming out, we reverse it, and the stereochemical configuration here is actually R. So that's something that you want to keep in mind, is that the hydrogens, when they are horizontal, they're coming out towards you. And if it's the lowest priority group, you have to reverse that stereochemical configuration. So I'm just going to erase all this spinach that I put on here, and we're going to write next to Dglyceraldehyde, we'll put that it is, in fact, an R molecule. And then over here we have Lglyceraldehyde, which is S. Now, something that we're going to talk about throughout this chapter are D and L sugars. And if you're wondering about Dglyceraldehyde, okay, why it says positive over here, well, remember the positive next to glyceraldehyde is because it rotates plane polarized light in the dextrorotatory direction. It rotates it clockwise, okay? The plane polarized light is rotated clockwise. So we're going to talk a lot about D sugars in this class, okay? We're going to talk a lot about D sugars. The reason why is because D sugars are naturally occurring. These are the sugars that are formed in nature. So naturally occurring, okay? And how do we know when something is a D sugar, like Dglyceraldehyde? Pay attention. It's when the hydroxyl group at the chiral center, farthest away from the carbonyl, whether it's an aldose or a ketose, is on the right-hand side of the Fisher projection, okay? So if we look at Lglyceraldehyde, there's only 1 chiral carbon, and you see that the hydroxyl is pointing off to the left, so that proves that it's not a D sugar, Okay, it's an L sugar. If you look at all of these sugars down here, ribose, glucose, and fructose, they're all D sugars. Why? Because if you look at ribose, for example, you see the chiral center, that's the furthest away from the carbonyl, right? This is not a chiral carbon because that carbon has two groups that are the same, the two hydrogens. But that chiral carbon, this one here, furthest away from the carbonyl, the hydroxyl is on the right-hand side. Therefore, it's a D sugar. It's a naturally occurring sugar. If you look at D-glucose and D-fructose, these two Fisher projections that are drawn, again, the hydroxyl that's on the chiral center furthest away from the carbonyl, whether it's an aldose or a ketose, since they're on the right-hand side, these are D sugars. Now, if that isn't enough for you, I have more. All right. Now, the fact that Dglyceraldehyde rotates plane polarized light clockwise, that has nothing to do with whether the compound is R or S or D or L. Okay? So just because these are D sugars, it doesn't necessarily mean that they're going to rotate plane polarized light in the positive direction. It just so happens that Dglyceraldehyde rotates plane polarized light in the positive direction. So sometimes we'll call it D plus glyceraldehyde. Okay, and if you're still not 100% sure about what I'm talking about, we'll talk about it more as we go along here. Okay, but now we have a D sugar, which is naturally occurring, and we have L sugars like L-glyceraldehyde, which are not naturally occurring. And if you're wondering, well, if they're not natural, where do you get them from? Well, normally L sugars are going to be made in the lab. Okay, they would be made by a synthetic organic chemist who put that together. All right, so let's move on from there. And here's a little more information. It says, recall that dextrorotatory versus levorotatory has nothing to do with D and L. Okay, right? If you go back to our dglyceraldehyde actually rotates plane polarized light in the positive direction. Well, look at these two D sugars here, D-erythros and D-threose. They both rotate plane polarized light in the counterclockwise direction. So again, and I'm repeating this for like the fourth time, but I just want you to get this straight, that D and L, okay, has nothing to do with whether the molecule is going to rotate plane polarized light in the positive direction or the negative direction, or counterclockwise direction. Okay, clockwise or counterclockwise, there is no correlation. Okay, D sugar means nothing more that the configuration of the chiral center is R. The furthest chiral center, I should say, is R, and the L sugar has the S configuration at the furthest chiral center. Don't believe me? We could check. Okay, both of these should have R chirality at these chiral centers. Okay, so let's just try one of them just for fun, and then you can try the other because we covered this way back in chapter 5. But let's just look at this chiral center here. If you're a little rusty on your Kahn-Ingold pre-log rules, right? The hydroxyl, we have oxygen, that's going to be number 1. The hydrogen will be number 4. We have a carbon here and a carbon down below. This carbon is attached to oxygen, carbon, hydrogen. This one is attached to oxygen, hydrogen, hydrogen. So this is the winner. So this will be carbon number 2. This will be number 3. So we go from 1 to 2 to 3 around the stereocenter. We're going counterclockwise, which would be S. But since the hydrogen is coming out, this stereocenter is, in fact, R. So it's correct, right? It says, again, at the bottom, that if the hydroxyl is pointing to the right-hand side of the chiral carbon furthest away from the carbonyl, it has the R stereochemical configuration. All right, there we go. Well, it says here, determine whether each of the following carbohydrates is a D or L sugar. That shouldn't take long. And then we want to assign a stereochemical configuration to each chiral center. And check it out. There's even more here. It says, after you assign the configuration for all the chiral centers, do you notice any trend that could help you do it really quickly? Okay, to assign the stereochemistry really quickly. These take a while, so let's just try the first one for now, and then you can try the rest at home. Once you know how to do one, it won't take too long to do the others. But let's take a look at the first one, okay? Remember that, well, let's answer the first question first, okay? It says, are each of the following compounds D or L sugars? Could anybody tell me about A? Would this be a D or L sugar? And it's not me trying to trick you or pull a fast one on you. Yeah, thanks, Gilbert. It's a D sugar. Absolutely. You're 100%. Everybody's 100% correct. What about the other two? What about B and C? Yeah, thanks, Gilbert. Gilbert says they're all D. He's 100% correct. You can see here, here, here. So all are D. Okay, all are D sugars. See, that didn't take too long. Okay, well, let's go back to the first one and see if we can assign the stereochemical configuration. We said that this one should be R, right? Because we said if the last hydroxyl is pointing to the right, it's R. Well, let's just double check. So this would be 1, this would be 4. This one would be, so this is oxygen. So this is number 2, this is number 3. So this is going like this. We reverse it. So yes, that's correct. This one is R. Let's go back up to the top. So we'll do the one at the top next. So we'll do this one right here. So we have 1, we have 4. This carbon is attached to oxygen, oxygen, hydrogen, and this one is attached to oxygen, carbon, hydrogen. So this is number 2, and this is number 3. So we go from 1 to 2 to 3. So that's clockwise, which would be R, but we reverse it, so it's S. So let's scribble that out. And we have, come on, we have S here, S. Next one, this one here, we have number 1, we have number 4. This carbon is attached to oxygen, carbon, hydrogen, and this carbon is attached to, dang it, oxygen, carbon, hydrogen. So we have to keep going. Then you can see that this one is going to be the winner after that. So we have 1, 2, and 3 going this way. So we're going like this, which is R, but we reverse it so that it's S. Does anybody notice a trend here yet? Maybe not. Let's try this one here. Try the last one. I'll use the black pen for this one. We have 1, we have 4, we have 2, and then we have 3. So we're going like this, which is counterclockwise, which is which would be S, but we reverse it, and so it's R. And so the shorthand that you're supposed to notice when you do all of these is nothing more than this. If the hydroxyl is on the left-hand side, it's S, and when it's on the right-hand side, it's R. So we'll put here S is for when OH on left-hand side, and R is when OH is on right-hand side. Okay, that's the shorthand for designating these. So you can do it pretty quickly. So you can see that all 3 of these would all be R, and then over here, these 2 are R as well. So there you go, R, and that's the shorthand right there. Boom. I bet you're wishing, you're like, man, I wish there was more rules like this in organic chemistry. You just remember that the one on the left-hand side, and you think left means sinister, or sinister means left, you know. Well, S, you know, you can think about it that way. Anyhow, kind of fun there. All right, let's move on, and let's talk about the configuration of an aldose. So let's talk a little bit more about aldoses. We've talked about what a ketose is and what an aldose is. And an aldose is when we have an aldehyde in our monosaccharide, right towards the top. We always write the most oxidized carbon at the top of our Fisher projection. It's always going to be written that way, that the most oxidized carbon is put on the top of the Fisher projection, or towards the top. So it says here there's 4 possible aldotetroses, right? Aldo meaning aldehyde, and tetros meaning 4 carbons. So you can see we have 1, 2, 3, 4 carbons here, and 1, 2, 3, 4 carbons in this compound. So remember, the formula was 2 to the power of n, where n is the number of stereocenters. So if we have 2 stereocenters, it's 2 to the power of 2, which equals 4, right? So that means we have 2 stereoisomers that are D sugars, and these aren't diastereomers, or these aren't enantiomers, they're diastereomers. But then we have the 2 enantiomers, one of each of these, right? and those are the L sugars. So the enantiomers of each of these would be L-erythros and L-threose. And you can practice drawing those, just the mirror image. You just have to change the stereochemical configuration of these two to make L-threose and change both of those to make, sorry, L-erythros here and L-threose here. Anyhow, there you go. And if you're, again, wondering why we don't put the L sugars up here, why is everything about D sugar this and D sugar that? It's because D sugars are the ones that are found in nature. They're the ones that are abundantly found in nature. And so, you know, we just don't worry about L sugars nearly as much. So again, if you want to practice drawing one of the enantiomers just for fun, let's draw the enantiomer of L-erythros. So just draw a line here. So we're going to start out, we have our carbonyl at the top, okay? Then we have our CH2OH down here. There we go, and there we go. So we just draw the mirror image. We reflect the hydrogens and the hydroxyls, and we're done. And this is L-erythros. And that's how you draw an enantiomer of a sugar. Just give me 1 second here. All right. There we go. Well, what about Ronaldo pentose? Here we have 3 stereocenters, right? We have 1, 2, 3. So that means we have 2 to the power of 3. So that's 8 possible stereoisomers. We have 4 D sugars, and we would have 4 L sugars. Now again, here we only have the L sugars shown on here, and those are ribose. And that's the same ribose that's found in DNA, like deoxyribose. Next we have arabinose, xylose, and D-lysose. You do not have to have these memorized by any stretch of the means. If you need the structure of a carbohydrate, except for glucose, I think it's a good idea to have that memorized. But outside of glucose, there are no aldoses that you have to have their structures memorized. Well, if we keep going up to an aldohexose, this is a typo here. It shouldn't say hextose. There's no such thing. It's an aldohexose. They have 4 chiral centers, so we have 2 to the power of 4, which is equal to a total of 16 possible stereoisomers. We have 8 D stereoisomers, and then we have 8 L stereoisomers. So we go from allose to ultrose to glucose, mannose, glucose, idose, galactose, and talose. Again, I don't expect you to memorize any of these, except, you know, I always thought it was a good idea for students to memorize the Fischer structure of glucose. It's really handy. Even if I teach this at the nursing level, I ask my students to memorize the structure of glucose. Why? Because it's the most abundant monosaccharide on the planet Earth. Probably a good idea when you're in organic chemistry to have that feather in your cap. So this is what we call the family of aldoses. So we start with glyceraldehyde, and you can see that all we do as we go from a triose, glyceraldehyde, to a tetrose, to a pentose, to a hexose, all we do is increase the number of carbons, right? So we add a carbon here, and then we flip it, right? And then we take deerythros, we add a carbon onto that, and we flip it, right, to get a pair of diastereomers, and so on and so forth. So this is the family. We would call this the family of D aldoses, okay? And notice what they all have in common. They all have the hydroxyl in blue, the one that's on the chiral center furthest from the carbonyl, and it is pointing to the right. It has the R stereochemical configuration. There we go. All right. So, and if you're wondering, well, can't you keep going? Can't you go down to a heptose? Yes, but we're not really going to stress about that in Chemistry 3111. Now, for ketosis, we start with the simplest possible ketose, which actually has no chiral center in it, unlike glyceraldehyde, which is a which is a triose, right? It has 3 carbons. Well, this is a keto triose. It has 3 carbons, but it has no chiral center. So as you go from a triose to a tetrose to a pentose to a hexose, when we're dealing with ketosis, there's always going to be 1 less chiral carbon than there would be with the aldose with the analogous number of carbons. So we start with dihydroxyacetone. Easy to remember. Everybody should know the structure of acetone by now. It's this molecule right here. All you do is you add a couple of hydroxys to it, like that, and there you go. That's dihydroxyacetone. And from there, you just start adding the chiral carbon. So we have erythrulose, okay? And you notice that ribulose and xylulose, they all end in ulose. And then the rest are a little bit more complicated to remember. Here we have psychose, fructose, which is fruit sugar, very commonly found in fruits. It's very sweet. It's sweeter than table sugar. Then we have sorbose, which is also a sweetener. There we go. And what else? We have tagatose down here. So again, I don't ask you to memorize any of these specifically, but you should know that fructose is a ketose, whereas glucose is an aldose. Sucrose, which is table sugar, is actually a disaccharide, which comes from fructose and glucose, and we'll look at its structure later on. But again, these are the naturally occurring ketoses. These are the D-ketoses. There are L-ketoses, but those are unnatural, and we would probably form those in a lab if we needed them. Just as an aside, you know, the naturally occurring ketoses and aldoses are all D, okay? Well, later on, we're going to look at amino acids, and the naturally occurring amino acids are L amino acids, which is a little frustrating, but things can be like that in science sometimes. Anyhow, here it says draw and name the enantiomer of D-fructose. Now, again, this is one of those questions where I don't expect you to be able to regurgitate the structure of D-fructose, off the top of your head. So I would give you that structure, but I'm just going to write it down here quickly, and then we'll draw the enantiomer. And I already showed you how to do this earlier today. So here is, this is D-fructose. So let me just finish here. So D-fructose, okay. And then to draw the enantiomer, so I would give you this. To draw the enantiomer, all we do is, I'm actually just going to copy it and paste it. I think that would be the fastest thing to do. So copy, and then we'll paste it. And all we have to do is invert the stereocenter. So I'm going to erase everything that's on a stereocenter, and we're just going to invert them all, and we'll leave all the rest the same. So L-fructose. And if you're wondering, like, why aren't you inverting that? Well, this isn't a stereocenter, is it? Right? This isn't a stereocenter. This isn't a stereocenter, so I'll leave it the way it is. So put the hydrogen here, hydroxyl here, hydroxyl here. And there you go, my friend. That's all there is to it, to drawing the enantiomer of D-fructose. Give me a thumbs up if you think you could draw the enantiomer of a sugar like fructose. Cellulose is not a ketose. Cellulose is an aldose. Okay, so cellulose is a polymer of glucose. So it's a polysaccharide. And I see that you're saying, why do we begin the name of some sugars with Greek letters, like beta lactose or alpha lactose? Well, that's not a sugar. That's a disaccharide. But we're going to talk about that later on. Okay, that's all based on the first carbon of the closed chain form of a monosaccharide. Okay, we'll talk about that later on for sure. We're going to start it right here, as a matter of fact. So the cyclic structure of monosaccharides. Everything that we drew so far was in an open chain form. Okay, so if we go back to these families here, when they're all drawn like this, these are called an open chain form because we have just a linear chain. So these are all, could write it in here, open chain. Okay, and the same thing back here. If we look at the family of aldoses, these are all open chains, right? There's no rings here anywhere. But what happens is those open chains can form rings depending on the situation. And it says here that an aldehyde, if you remember, way back when we talked about acetals and hemiacetals, if you take an aldehyde and you put it in the presence of an alcohol with a catalytic amount of acid, we can produce a hemiacetal. Now, the equilibrium is usually going to lie to the side of the starting materials, except for certain situations. And one of those situations would be when we form a cyclic hemiacetal that has a 6-membered ring, right? 1, 2, 3, 4, 5, 6 members in this 6-membered ring. So we're forming that cyclic hemiacetal. Again, it's got a 6-membered ring, and 6-membered rings are pretty stable in organic chemistry. Right? Remember that the reason why this is a hemiacetal is because this carbon has an ether attached to it and a hydroxyl, right? It's got an R group here. It's got a hydrogen here. It doesn't matter if that's an R group or a hydrogen, but this is a hemiacetal, and it is a cyclic hemiacetal. So what's the consequence of this point right here when it comes to sugars? Well, let me show you. If you have a compound like D-glucose, and that's what's shown right here, we have D-glucose. Well, what happens is one of the lone pairs on the hydroxyl at carbon 5 can react with the carbonyl on carbon 1, and we end up forming this closed chain form here. So all they've done in this is that they've taken the open form, which is both of these, okay, and they're showing the proximity of that hydroxyl on carbon 5 to the carbonyl carbon on carbon 1, of course, okay? If you look at this Fisher projection here, it's not clear that this and this are close to one another. But when you draw it in this conformation that's shown right here, you can see that they're pretty dang close enough to do this, for the lone pair to come in here like this, and then we do a proton transfer, and we end up with a closed form. And we call this a pyranose or a pyranose. I usually call it either one, I guess, but this is a pyranose or a pyranose, and it's named after the molecule pyran, which is this molecule here. This is called pyran, anyhow, which is neither here nor there, but it's a good idea to know where words come from. So here's the pyranose form, because we have that 6-membered ring that has the oxygen in it. Notice that in this Haworth projection, notice that the oxygen is in the top right corner, and that is a convention. Whenever we draw the Haworth projection of a hexose, we always draw it with the oxygen in the top right corner. Okay? Anyhow, there we go. So what happens is when that cyclization occurs, we can end up with 2 different stereoisomers, which are technically diastereomers, and I'm going to explain why. The reason why is because when this nucleophilic attack that I have drawn here, okay, this can occur from the top face of the molecule, or it can occur from the bottom face of the molecule. So like this. And depending on which face of the molecule it attacks, the new hydroxyl that's formed can either be pointing up or down. Okay? If it's pointing down, this is called the alpha position. You can think of that as like alpha looks like a fish, okay? And fish live under the water, so you think alpha is going down. And then if it's pointing up, we call that the beta position. You think of that as like beta. You can take a beta and you can make a butterfly, and butterflies live up. They live up in the sky. And that carbon 1 of that pyranose ring, we call that the anomeric carbon. Very important in carbohydrate chemistry, the anomeric carbon. So you can see that all the stereocenters, 2, 3, and 4, and 5, right? Look, 2, 3, 4, and 5, all their stereochemical configurations are identical. The only difference between these 2 molecules is the stereochemical configuration at carbon 1 only. And so we call these anomers of each other. And if you're wondering, well, aren't those diastereomers? Yes, they are, okay? But they're just diastereomers that are formed upon cyclization, and we call them anomers because they differ in the stereochemical configuration at the anomeric carbon only. So again, the alpha anomer, you have the hydroxyl pointing up. Here it says the alpha, it's pointing down. You say it's trans to the CH3OH group, and then if it's the beta, it's pointing up, or you can say it's cis to that same group. So anomeric carbon, very, very important in carbohydrate chemistry, the anomeric carbon, that you know what it is. And before we move on, I want to just point out one more thing, okay? This, what you have shown here, that's a Haworth projection, right? And Haworth projections are really important, but remember that when you're an organic chemist, it pays to be able to observe a molecule from different ways, right? And we know that each one of the carbons and the oxygen in the six-membered ring, they're all sp3 hybridized. And so that's why it's helpful sometimes to look at this molecule or these molecules that are shown here, to look at them in a chair form. So if you were to draw a chair form of this molecule, it would look like this. Okay, this is not a very good chair. Let me see if I can improve that chair. So it would look maybe more like this. Okay, like that, and then put the oxygen up here. And what's interesting about beta D-glucose, so this is beta D-glucose, right? Why? Because it's D-glucose, and the hydroxyl on the anomeric carbon is pointing up, so it's beta. The interesting thing about beta D-glucose is this. If I draw the chair this way, the way I have shown on here, okay, like this, let's take a look. The hydroxyl is pointing up, so that means it would be up and equatorial. The hydroxyl on carbon 2 is pointing down, so it would be down and equatorial. The hydroxyl on carbon 3 is pointing up, so it would be up and equatorial. The hydroxyl on carbon 4 is pointing down, so it would be down and equatorial. Then you have this CH2OH group pointing up, so it would be going up and equatorial, CH2OH. And so what's cool about beta D-glucose is that every single substituent, even the hydroxyl at the anomeric carbon, everything is equatorial, okay, which is kind of cool. And that's why glucose is the most abundant carbohydrate. It's because all the hydroxyls are equatorial, except for in alpha D-glucose, in which case this hydroxyl would be pointing down. Okay, so kind of cool. Anyhow, so let's take a look at the concept of MUTA rotation, which is this. Okay, now it says here we have 0 or less than 0.01%, and in fact, when you put glucose, for example, in water, okay, it actually exists in an equilibrium. Okay, we have the alpha D-glucopyranose, so where the hydroxyl is pointing down, that actually exists in about 37%, okay? And then we have the rest of it, so the other 63% is going to be the beta. So the point is this, is that if you were to take, so see if you can follow along with me, and the book goes into probably a little more detail than what I'm going to tell you. If you're to take pure alpha D-glucose, okay, 100% pure alpha, it's crystallized, there's no beta, you put it in water, what happens is that after not very long, it's going to equilibrate, and you're going to end up with a mixture that's 37% alpha and 63% beta. Same thing, if you take only pure beta and you put it in water, all of a sudden you're going to get an equilibration where you end up the same percentage of the alpha and the beta anomer. And the process with which they interconvert the alpha and the beta anomers is called MUTA rotation. And the reason it happens is because the pyranose forms, okay, these forms here, they can open up, okay, they can open up to give you the open chain form, which is shown here. Now, you don't need very much of it, okay? Even if you have a little bit, it's going to still cause that equilibrium to occur, okay, which is kind of interesting. But that's the process of MUTA rotation. So if you're wondering, it doesn't sound like it's even all that useful, to spend all this time maybe crystallizing it or whatever, which maybe it isn't. But, anyhow, it's kind of interesting. All right. And if you're wondering, like how would you follow this equilibrium? Again, the textbook goes into a little bit more detail about it. But basically, if you have the pure alpha anomer, its optical rotation is plus 112, come on, plus 112.2 degrees. And the optical rotation of the beta, so of the beta is 18.7 degrees. And again, what happens is when you have a mixture of both, right, the alpha and the beta, and 37 and 63% respectively, it's always going to come out to give you an average, not exactly a 50-50 average, but you're always going to end up with an optical rotation which is 52.6 degrees. Okay, so it's always gonna, you're always gonna end up with that no matter how hard you work. But anyhow, that's the concept of MUTA rotation. Another thing about MUTA rotation is that it's not always possible to determine by inspection which pyranose, whether it's the alpha or the beta, is going to predominate. Okay, so you can't just say, well, because the hydroxyl here is equatorial, it's going to predominate. It's not that easy. It's actually much more complex than that. And so you can't always tell. But since since D-glucose is the most common monosaccharide, they're just kind of showing you an example and familiarizing you with the term MUTA rotation that's all that's happening here. All right, so again, the dynamic equilibrium between the alpha and the beta, we call that MUTA rotation. It can be accelerated in the presence of acid or base, so it can be sped up a little bit. And it says here, again, like I was just telling you, the last thing I told you is that you can't tell which one is going to predominate. For some sugars, alpha is going to predominate. For others, beta will predominate. There's no way to just predict just by looking. Okay, I recommend trying this skill builder here, where you get some practice in drawing pyranose anomers and messing around with that and being sure that you're able to do it. But I think something that's even more important is to be able to go from a Haworth projection, like is shown right here, and be able to take that and draw a chair. And I did it for you earlier on today, okay? Just a few minutes ago. I said that whenever you draw a Haworth projection, you always draw the 6-membered ring so that the oxygen is in the top right corner, okay? And we always number the carbons like this: 1, 2, 3, 4, 5, 6, okay? The 6th one is, I'll put the hydroxyl on it, okay? But this is carbon number 6. You also need to know how to draw the chair form, okay? And this is the chair form. I'll try to draw a decent chair here, okay? And the numbering here for the carbons is 1, 2, 3, 4, 5, and then you have the CH2OH. We can just draw it the way they have it here, CH2OH. This is carbon number 6. So what I have highlighted up here and here are identical, okay? And you need to know how to draw both. Remember that on a chair, you've got to be able to insert substituents and determine whether they're going to be axial or equatorial, right? If this is carbon number 1, 2, 3, if the hydroxyl on carbon number 3 is going up, you have to know that it's up and equatorial, right? You've got to be able to put that in. And again, I demonstrated that just a few minutes ago, but you've got to be able to do it. Now, something else that I mentioned is that the reason why, and what's drawn here, this is beta D-glucose, but the reason why D-glucose is the most abundant sugar on the planet is because all the groups are equatorial. Not necessarily the anomeric carbon, that depends on whether it's alpha or beta. Beta is equatorial, alpha is axial, but the rest of the hydroxyls and the CH2OH, those are all equatorial, and that again is why glucose is so naturally abundant. Let me give you an example of a sugar that isn't as abundant. And this is just kind of an aside. I didn't plan on doing this, but if you draw this sugar, okay, so I'll just make beta here, okay, and if we put this, like for example, this is one of the few that I have memorized. So if we have CH2OH over here, this is beta D-galactose. Galactose, okay? And the reason why galactose isn't as abundant as glucose is because you have one of the hydroxyls being axial, okay? And galactose is found in lactose because lactose is a disaccharide that is made from glucose and galactose. And we'll look at its structure later on today, okay? You see why you spent all that time in Organic Chemistry 1 practicing drawing chairs? Well, it wasn't for nothing, was it? Right? It's coming back to you now towards the end of Organic Chemistry 2 when we look at carbohydrate chemistry. And I know a lot of you are interested in studying biochemistry, and it's going to come up then as well. Well, besides a pyranose form of a monosaccharide, we can also form a 5-membered hemiacetal, so a 5-membered ring that has a hemiacetal of a sugar. And that is not a pyranose, that's a furanose, okay? And a furanose ring would come from something like fructose. Okay, so fructose is a ketohexose. Now, fructose, the book goes into quite a bit of detail about it here, but fructose has both, again, a furanose form, where it has a 5-membered ring, and then it also has a pyridose form. And you can see that here the hydroxyl is pointing up, so we have a beta furanose form, we have a beta pyranose form, we have an alpha furanose form, an alpha pyranose form, and the textbook goes into a little bit of detail about that. And it actually talks about something kind of interesting, which is that it's one of the pyranose forms that actually predominates if you look at a fructose in solution. However, it's the beta furanose form of D-fructose that precipitates or participates in most biochemical pathways. So that's just something that's kind of interesting there. All right. And here it is right here on my slides. I'm just not looking through them while I'm talking here anyhow. So something that I do want to point out here, though, is that the only time I'm going to ask you to take a Fisher projection and be able to draw a chair or a Haworth projection from it would be with an aldohexose. So since fructose is not an aldohexose, it's a ketose, I won't ask you to do it. So what am I saying? Again, I'm repeating myself a different way, but I'm not going to ask you to draw 5-membered rings from a straight chain form. Okay? Just not going to happen. All right? There we go. So let's do some questions, things that I would expect you to be able to do. Let me show you what I do expect you to be able to do. And I don't expect you to memorize what galactose is and what mannose is. I would give you those. But let's say you had this. So I'm going to draw the structure of galactose. So let me get this here. Okay, so we have 1, 2, 3, 4. So galactose is this, where we have a hydroxyl. There we go. There we go. And then I'm going to draw a mannose down here for anybody who wants to go ahead a little bit and doesn't want to listen to my whole gaudy explanation here. So just give me a sec. And again, you could look at the family of aldoses that's earlier in the slides. There we go. All right. So it says to draw the what? Draw the Haworth projection of each of the following compounds. So what we're going to do with our galactose is that, and again, this is just D-galactose that I have drawn here. So first we're going to number the carbons. We have 1, 2, 3, 4, 5, 6. Okay, so the first thing you're always going to do when you want to draw a Haworth projection is this. You're going to draw the 6-membered ring with the oxygen in the top right corner. There we go. You can shade in these ones if you want to, if you're a real artiste. Not that I am, but then you're going to number the carbons. So we have 1, 2, 3, 4, 5, and then we have 6. Okay? What I have here, this is constant. That will never change for any pyranose that you want to draw a Haworth projection of. It's always going to look like this. Now remember, the anomeric carbon, carbon 1, in the Haworth projection, it's going to be a stereocenter, but it's not a stereocenter in the open chain form. And so the reaction that's going to occur to make the hemiacetal, the nucleophilic attack by the hydroxyl on carbon 5 is going to attack that carbonyl, okay? And then we're going to make a chiral center. And so the beta here, okay, this indicates chirality at chiral, or at anomeric carbon, sorry, at anomeric carbon. And let me not put chirality, let me put indicates direction of hydroxyl. Okay, so since it says beta, that means the hydroxyl on carbon number 1 is going to be pointing up like that. If we look at carbon number 2, you can see that the hydroxyl is pointing to the left. So here's the shorthand. Let me show you Mr. Dion's quick and dirty rules. Anything that's on the right-hand side of the molecule is going to be pointing down. Okay? Anything that's on this side is going to be pointing up. So on carbon number 2, we have the hydroxyl pointing down. So let's draw it pointing down. On carbon number 3, we have the hydroxyl pointing up. So let's draw it pointing up. On carbon number 4, we have the hydroxyl pointing up. This. And that's it. Carbon number 5 is already taken care of because it's the one, the hydroxyl formed a bond, you know, there we go. So there you go, because the CH2OH is always going to be pointing up like that. Now, it didn't ask us to draw a chair here, but I'm going to do it just for fun. So it's going to mean that this is what our chair is going to look like. Okay, so we have the beta, carbon number 1. So let me number my carbons 1, 2, 3, 4, 5, and then I have CH2OH. So this is carbon number 6. So my beta carbon hydroxyl is pointing up. The next one is pointing down. The next one is pointing up. And the next one is also pointing up. And there you go. So these two both represent beta D-galactose. And the Fisher projection just represents D-galactose. Let's try it again. We'll try it with alpha D manopyranose. So we're going to start with our 6-membered ring, oxygen in the top right corner, a shade in here just to be all fancy. It's like the new Bob Ross here. There we go, 1, 2, 3, 4, 5, and then we have CH2OH up here. Okay, so it says it's alpha, so that means the hydroxyl on carbon number 1 is going to be pointing down. Also remember my shorthand, anything on this side is going to be going down. Anything on this side will be pointing up. So on carbon number, let's see, we got 1, 2, 3, 4, 5, 6. So on carbon number 2, the hydroxyl is going to be pointing up. So we draw it in the up position. In carbon number 3, it's also in the up position, like this. Carbon number 4, it's in the down position. And my carbon number 5, I already have the stereochemistry worked out there. So now if we want to draw a chair, we're going to do this. Draw a chair. We're going to do something like this. It's alpha, so the hydroxyl, the anomeric carbon is going down. We have 1, 2, 3, 4, 5, and of course we have 6 in the hydroxyl. So there we go. Carbon number 2, the hydroxyl is pointing up. So forgive me, but I'm just going to draw it going straight up like that. On carbon number 3, it's also pointing up. Okay. Carbon number 4, it's pointing down, so it's going to be down like that. And there you have it. That's it. That's alpha D manopyranose. Give me a thumbs up if you're like, I think I could do that. Just give me a minute to look at it. Don't expect me to know it in the first 10 minutes, which you don't. But do you think you could do that? Give it enough time? All right. Thanks, Gilbert. Okay. Let's try one more problem. Or maybe we'll try a couple more. Take a quick break and find where I was here. It says provide the complete name. No, got to find where I was. Here we go. It says provide a complete name for the following compound. So again, in order for us to name this, you know, we'd have to have the family of aldehexoses at our disposal. But let's give it a try here. So could anybody tell me if this is alpha or beta, first of all, just for fun? Yeah, it's beta. Yeah, so we get that. So this is beta. Anyhow, so look, here's how we're going to do it. We're going to start by drawing this. We're going to put our CH2OH up here. We're going to draw the things that don't change in our Fisher projection. Okay, so we have 1, 2, 3, 4, 5, 6. Remember that anything on this side is going to be pointing down, and anything on this side is going to be pointing up. So if we go to carbon 2, you see the hydroxyl is pointing down. So that means that on carbon number 2, the hydroxyl is going to be over here. On carbon number 3, the hydroxyl is pointing up, so it's going to be over here. On carbon number 4, the hydroxyl is also pointing up, so it's going to be over here. And then on carbon number 5, since we're always looking at D sugars, right, it means the hydroxyl is going to be over here like this, right? Again, this is going to be a D sugar because we're not concerned with any L sugars. And so if we put in all of our hydrogens like this, then we go over to the family of aldoses. Anybody recognize it? It's D-galactose. So let's go back here and we'll pencil it in. Come on, where am I? There you go. It is D-galactose. All right, let's try another one. It says, draw the more stable chair conformation for each of the following compounds. So we have beta-galactopyranose, alpha-D-glucopyranose, and then we have beta-D-glucopyranose. So for the chair conformations for the two glucopyranoses, whether it's alpha or beta, remember that I told you that with glucose it's kind of easy, and I just mean it's a little faster than the others because in a glucose everything is equatorial except for the anomeric carbon. So if it's alpha, that means the hydroxyl is pointing down, and every other hydroxyl is in the equatorial position. So we just put them here like this, and then we have our CH2OH like this. And I like to sometimes just draw it like this, CH2OH. I think it looks a little neater like that. But again, remember that with glucose, okay, all OHs are equatorial, except anomeric carbon. Okay, that's in alpha. And in beta, everything is equatorial, even the anomeric carbon. So to draw the beta, all we have to do is take this, and we're going to, oops, didn't do that. We're going to take it, and we're going to copy it and paste it. So copy, and we'll paste it right here. Okay, like that. And then all we're going to do is scribble this out. Okay, and then we'll put the hydroxyl in the beta position. It's going up like that. And there you have it, my friend. Nothing more to it than that. Now with galactose, okay, if we go back to the family of aldoses, we saw that galactose, we had this. And again, this is the kind of stuff I would tell you. You know, I'm not going to ask you to memorize the structure of galactose, but we just saw it a couple of seconds ago. It's kind of fresh in our memory. And this is galactose, like this. Okay, so we number the carbons, 1, 2, 3, 4, 5, 6. We draw our chair like this. That. There we go. It's beta, so the hydroxyl is going to be pointing up. On carbon number 2, this hydroxyl is on the right-hand side, so anything here is going to be going down. Okay, so the hydroxyl is going to be going down on carbon number 2, so it's going to be down and equatorial. On carbon number 3, the hydroxyl is going to be pointing up. It's up and equatorial. On the next one, it's up, but it's going to be up and axial. And then we have our CH2OH. And there you go. Now we've drawn the chair forms of all of these. And let's see, we had another one here. The next one just asks us to draw the open chain form of a chair. So we're asked to draw the open chain form of a chair. And if you look at your textbook, it goes into a little bit of detail about the mechanism of the ring opening. So it essentially does this, okay, where you end up opening the ring this way. And anyhow, you can look at that in your own spare time, because I'm not going to ask you to draw the mechanism of this at all. I think it's easier to just remember this. Just say, well, I've got my Fisher projection. I'm going to draw the things that never change. I have 1, 2, 3, 4 chiral centers. I know it's a D sugar because that's all we're interested in. I have carbon number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. On carbon number 2, the hydroxyl is pointing down, so that means it's going to be pointing on the right-hand side. On carbon number 3, it's also pointing down, so that means it's going to be on the right-hand side. On carbon 4, it's pointing down, so it's also on the right-hand side, and there you go. So that's the straight chain form like that, and this is D-allose. So we're going to take a short break now. When we come back, we're going to take a look at some interesting reactions of monosaccharides.